In our previous screencast, we talked about a concept called seafloor spreading, which happens at the mid-ocean ridge. And maybe it occurred to you like, well, wait a second. If we keep getting new material forming at the mid-ocean ridge, why isn't the world getting bigger? And that's where plate tectonics comes in. So basically, plate tectonics is the culmination of Alfred Wegener's idea. And it brings the theory of plate tectonics brings in so much evidence and so many concepts to basically explain how it is that the surface of the Earth operates in a dynamic way. So it all comes down to convection. So remember, convection we talked about earlier in the year is the upward movement of hot fluids because they're less dense, and the downward movement of colder fluids because they're more dense. Now remember, a fluid could be a gas like the air. We talked about that with the atmosphere. It also happens with liquids. It happens with semi-liquids. So in the mantle, convection is occurring because it's hotter near the core and cooler near the surface. So that means is we have these convection currents operating within inside Earth's mantle. Remember, the Earth's mantle makes up like what is it, like 80% of the world's volume? Is a lot of it, right? And so as these things churn and slowly move up and slowly move down, hot material goes up, cold material sinks. Remember that as they do that, they cause the mid-ocean ridge to form. They basically they're dragging material with them as they go side to side. So the ocean floor is being carried away from each other at the spreading center by the motion of these convection currents. So essentially, the motion of the mantle drags the lithosphere, the rocky outer part, the upper mantle and crust with it as it circulates. Now, where these convection currents reach the surface and then deflect outwards, that's where we get these mid-ocean ridges, which we're going to call spreading centers. So areas where the crust is being pulled apart and then filled in with liquid volcanic material. Now, these spreading centers include, as we talked about yesterday, the mid-ocean ridges. So the mid-ocean ridges, here's the mid-Atlantic ridge, and it basically is an underwater mountain chain that runs the length of the Atlantic Ocean, basically from pole to pole, just about. And anywhere along here, we'll find that there is a convection current that's coming up, and rock material is moving this way on this side and moving this way on that side, and it's carrying the crust with it, and new volcanic material is coming up there. Now here is a map I showed you the other day, but basically it's showing you all of the spreading centers of the world, essentially. So we have at least all the mid-ocean ridges. We can see that there's quite a few of them in the world. Here's the famous one moving up the Atlantic Ocean, but they're basically all over the place, okay? And they come in a couple of varieties, okay? Well, one's the mid-ocean ridge is one, but another one is the island of Iceland. So Iceland is essentially a place where the mid-ocean ridge comes to the surface, and there's been some postulation that perhaps this is because of a meteor impact. We're not sure, but one thing that's cool about Iceland is that you can actually go and see the mid-ocean ridge express itself as a surface feature, which it usually is always an underwater feature that most of us never get to see. But there are other spreading centers. And the other ones are called rift valleys, which are very common in Africa. So if you look at Africa, you'll notice there's strings of lakes that run up the eastern edge of Africa. And basically, Africa is being pulled apart by these convection currents. And although we don't have oceans in there yet, we already have lakes because there's this low-lying land. And eventually these rift valleys will reach the ocean. So for instance, if you go back in time, the Arabian Peninsula was connected to Africa. These were rift valleys that then got big enough that seawater flooded them. So here's what, if you were to go to Africa, you would see a rift valley that looks like this. You have a plateau, and then it drops very low down to sea level, or even below sea level. Like, for instance, the Dead Sea is in a rift valley. And what we have is often these lakes form in them, and eventually there's volcanic activity in here as mantle material is coming up, and basically this eastern part of Africa is moving outwards, and eventually this valley will connect with the ocean, and it will just basically be water from one to the other, and this part of Africa will have peeled off and end up in the Indian Ocean. So again, as the mantle pulls the two slabs apart, magma is going to come up in between there to fill it up. So what we find is that we tend to get a lot of volcanic activity in rift valleys and in mid-ocean ridges, but this tends to be very gentle volcanic activity, and here's why. It's an easy concept. What makes volcanoes violent? What makes them explosive and dangerous? Well, usually what that means is there's a lot of gas there. Gases are what explode. And the two main gases that are going to make a volcano explode are steam, water vapor, or carbon dioxide. Well, it turns out neither one of those occurs in great abundance in the mantle. So the mantle material, when it gets to the surface and erupts, it tends to not have a lot of oomph to it because it just doesn't have much in the way of dissolved gases. But now here we can take a look real quick at it. I mean, it's so gentle that you can actually go down in a submersible and be right above it. So this is kind of a cool thing. This is the mid-ocean ridge and the mid-Atlantic ridge. A submersible went down there to film it. And I'm going to try to fast forward to the part where it actually occurs. Okay, here we go. I just want you to see this. This is really cool.
At its heart is a central crevasse, a rift between plates of the Earth's crust. As these plates move apart, they expose the fiery heart of the planet. But despite the fact that up to 95% of the world's volcanic activity occurs on the ridge, almost no eruptions have ever been witnessed here, let alone studied or sampled.
So that's pretty cool.
This film from an eruption more...
Oops. How do I make this stop? Okay. So I need to go to the next one. I hope I can make that happen. Let's see. Okay, now this is a film from one of the African rift volcanoes. I believe this one is Nyiragongo. And my son actually hiked this. This is in the Democratic Republic of Congo, and it is that's quite something here. I just wanted to see here that we'll do it as a narration. So we're just going to fly in and we look down and we see this is a volcano. So it's not just a rift valley, it's a volcano in a rift valley. And there's this fire lake. And so you notice you can actually get right up to it and look at this thing. You can just look at this steaming cauldron of lava, but it almost never explodes. Sometimes it runs down the side of the mountain, but it never really explodes. And the reason it doesn't explode is because there's not a lot of gas behind it. Let's see if I can make this go away. Come on, go to the next one. There we go. Okay. Now, the other thing about these spreading centers is it tends to be a place where we have a lot of earthquake activity. But remember, earthquakes happen when rocks move past each other, but since they're not moving past each other, they're actually moving away from each other. It's very gentle earthquake activity. It's the most common earthquake activity on the planet. Thousands and thousands of times a day, there are earthquakes along the world's mid-ocean ridges, but they're very small magnitude ones. They're almost unfeelable, like magnitude 2 or less. And that's because the rocks are moving apart rather than moving side to side next to each other. So here's an earthquake map of the North Atlantic. And you'll notice there's just so many earthquakes that happen along this mid-ocean ridge. I mean, there's some that happen in other places too, to be sure, right? Every once in a while, right? But the mid-ocean ridge is highly active because it's constant. Every time lava comes up and then pushes it apart, there's a little small earthquake occurs. Here's an earthquake map of Africa, and you can see the rift system quite clearly going from here to here with a side branch here, right? So we basically have this main rift system, and we have this rift system here. And remember I said the Arabian Peninsula, this is a rift system that has now been flooded by seawater, forming an ocean body of water. I'm embarrassed I forgot the name of it. I don't know. Is that the Red Sea? I don't know. The Arabian Gulf. I don't know what it's called. Okay. That's embarrassing. Eric. Okay. Now, so the other thing is, remember, when hot metal material comes up and moves outward, that's where we get our spreading centers, the mid-ocean ridge or rift valleys. But it also gets cold and it sinks. And when it sinks, it tends to pull the crust of the earth back down into the mantle. And that's why the world doesn't get bigger. I may make more material here, but I gobble it up over here when it sinks back in. Now, regions where we have sinking crustal material or lithospheric material. Remember, the lithosphere is just the crust in the upper part of the mantle. We call these things subduction zones. So when you just think submarines go under, subduction zones are where crust goes under. And basically, it can occur in different places. They always occur in the ocean, subduction zones, because it's only ocean plate that can go under. Continental crust is too buoyant and too thick to be pulled under. But uh, uh, the crust of the seafloor crust is capable of doing that. Now, so it forms where it goes down. It forms these trenches. So a trench. And we talked about those yesterday as a seafloor feature, but we didn't have an explanation for them. Now we know a trench is basically where the ocean crust is sinking down inside the earth, and it leaves this deep, trench in the ocean. And instead of being about 5,000 meters like the abyssal plains, it goes down to about 11,000 meters. And you see these things all over the world's oceans. So look at this. Here are trenches in the Pacific. Here's the Aleutian Islands. So here's Alaska. And here we have trenches here. We have trenches here, trenches here. Here is the coast, the west coast of South America. And we see we have trenches all the way here. Here's Central America. We have trenches here. So anywhere you see a trench, you have material sinking down into the mantle. Now, subduction zones tend to produce very violent earthquakes, and the reason there is, unlike the spreading zones where I'm pulling the rock apart, here I'm getting rock. Let's see, I'm getting rock to scrape under other rock, and as it scrapes past, that's what makes these earthquakes. So we tend to associate powerful earthquakes with subduction zones. Now, what's interesting here is that when you look at these, the depth of them helps us map out where this subducted material is, because what we find is we almost never find any earthquake activity in towards the ocean side of the trench. It tends to be more on the plunging side of it. So we have a trench, and immediately on one side we'll start to get earthquake activity, shallow, then getting deeper, and then getting deeper, and then getting deeper. And so we find is that here's a great example of it. So this is the coast of Peru and Chile. Here's Bolivia and Paraguay. And if you look in this map here, we're using shallow ones in light purple, lavender, followed by blue, which is a depth of about 33 kilometers, followed by green, which is up to 150 kilometers in depth, followed by yellow, which is a depth of about 300 kilometers, followed by red, which gets us down to about 500 to 800 kilometers. And so we can tell that what that means is that this crustal material is moving this way. It's sinking down this trench, and it's melting as it goes this way. I'm sorry, it's causing earthquakes to go that way. We're not talking about melting yet. Now let's talk about melting. Okay, so what happens is we find that the limit of these earthquakes is about 700 kilometers. Below that, we don't find earthquakes anymore. The reason is simple: that it's starting to melt, and you don't. Earthquakes happen when rock grinds past rock, but that once it melts, it just oozes past. So we find as the earthquakes happen in this part of the plunging ocean crust. But once we get down to a depth of about 700 kilometers, 700 kilometers deep, that is, we find that it's beginning to melt, and completely melted. So there's no more earthquakes at that point. Now, subduction zones are associated with very violent volcanic activity. Unlike mid-ocean ridges and rift valleys, which have fairly gentle volcanic activities, the volcanic activity associated with subduction zones, these are the volcanoes you think about, the ones that just explode and cause all kinds of damage and death. And it makes sense, and here's why. Okay, so what we have is this. As this lithospheric material moves down, it begins to melt. At first, it's just there's certain parts of it, the lower melting point things, the presence of water and carbon help it melt. And so, at this depth here, it begins to melt. And as it melts, the magma, the liquid melted rock, is less dense than the rock around it, which is heavier and solid. So it tends to move slowly upwards, basically convecting. And when it gets into surface, then it forms a magma body, and it erupts to the surface. Now, the reason they're so explosive compared to mid-ocean ridges and rift valleys is because of this. These things have a lot of water entrained in them, all right, because they're at the bottom of the ocean. And not only the water, basically, as it melts, it makes steam, and steam makes explosions, okay? But another thing is there's a lot of pelagic sediments. And those pelagic sediments are primarily made out of calcium carbonate shells. Well, calcium carbonate is CaCO3, and that breaks down under heating into CO2, which is a gas. So we also get a lot of carbon dioxide gas. So those are the reasons why we expect to find subduction volcanism to be much, much more explosive because of the presence of water vapor and carbon dioxide from the ocean sediments. Now we find is that these volcanoes tend to form about 300 kilometers away from the trench. So if this is the trench, we find if we go about 300 kilometers in the plunging direction, that's where it's going to happen, because it takes about 300 kilometers of horizontal motion before it gets deep enough down here to get to where it's starting to melt. All right, so we typically find where there's a trench so if there's a trench here, we go about 300 kilometers in, and we tend to find volcanoes. Whether it's, and we haven't talked about these different types, but when this happens in the ocean, we call these things island arcs. So we get these chains of islands. These trenches tend to be curved shaped, so arcs. So let's just take a look. So Japan, Indonesia, the Aleutians, I could go on the Caribbean, and there's so many of these in the world. I'll just look at a couple of them here. So here's a trench in the Western Pacific. About 300 kilometers in the plunging direction, you have the islands of Japan. Here is a trench. I'll put this out of the way. This is the Aleutian Islands. Here's their trench. About 300 kilometers in the plunging direction, we get volcanic activity. The Aleutian Islands, in case you didn't know, are highly, highly volcanic. Now, when I have ocean materials sinking underneath the continents, I still get volcanoes. I'm not going to get island arcs because I'm not going to get islands, but I will get what we call a volcanic arc. And it will, again, be about 300 kilometers in. One difference, though, is that we'll get folded mountains because this continental crust, it has a tendency to crumple when this, under the pressure of this. So we tend to get folded mountains with volcanoes embedded within them. And my house is located right about here. This isn't quite drawn correctly, but I'm right about here. So I live in the state of Washington, and we have the Cascade Mountains. And look, there's all kinds of volcanoes in those mountains. These are folded mountains for the most part. Most of them are not volcanoes, they're folded mountains. But there's also volcanoes in there. And if you go about 300 kilometers this way, what do you hit? A trench, which is sinking underneath the states of Washington, Oregon, and California. Okay, we already said that. All right. So now look at this. Here I have an earthquake map of the world. And it's kind of startling, when you look at it. It is kind of cool. You can see where the things are plunging, where it's getting deeper and deeper. But if we just look at it, it starts to look a bit like a puzzle. And so based on this, people were able to say, well, you know what? The world is basically broken up. It's like if you took a hard-boiled egg and cracked it, you've got several pieces, about 14 pieces that make up the surface of the world. And we call these things tectonic plates. So you can see here's a boundary, here's one plate. That's called the African plate, all right? This is called the Nazca plate. Here's the North American plate. Here's the Eurasian plate. Here's the Australian plate, and so on. Here's a volcano map of the world. You notice the volcanoes tend to be pretty much right where all the earthquakes are. Why? Well, because most earthquakes either occur at mid-ocean ridges or they occur where we have subduction going on. So if I look at a volcano map of the world, again, I see a similar pattern. So this brings us to the concept of plates, tectonic plates. So we have the world broken up into 14 of these plates, and they fit together like pieces of a puzzle, and they're bounded by one of two things. They'll be bounded by one of three things, but usually two things: a mid-ocean ridge, or they'll be bounded by a trench. There's also a couple places where we have a transform boundary. We'll talk about that in a minute. But for instance, here's the North American plate. The North American plate extends all the way out to the middle of the Caribbean. And it ends over here, just off the coast of Washington, where we have a trench. So the boundaries between these plates are where the action occurs. That's where we have volcanoes. That's where we have earthquakes. So it turns out there's three types of boundaries, of plate boundaries. We can have divergent, where they spread apart. That would be rift valleys and mid-ocean ridges. We have convergent, where they're coming together, subduction zones for the most part. And we can have transform, where they're sliding past. All right, and those are fairly rare. There's only one really famous one of those. So let's just talk about divergent plate boundaries. I mean, if they're diverging from each other, the plates are moving away from each other. That happens at mid-ocean ridges. And what we associate with that is gentle earthquakes and mild volcanic activity that's not particularly explosive, because it's mantle material that's coming up there that doesn't have a lot of water or carbon dioxide in it. Then there's transform boundaries, and really the most famous one of these is the San Andreas Fault of California. It extends basically from the Gulf of California, or the Sea of Cortez, whichever you want to call it, up to San Francisco, or just north of San Francisco. And here's the surface expression of it. And basically, this side of California is not associated with the North American. It's not part of the North American plate, and it's moving. It's part of the Pacific plate, and it's moving northward relative to the North American plate. Now we don't expect to have volcanoes here because there's nothing being moved down and melting. So since there's no subduction, there's nothing's being pushed under to melt. These are not associated with volcanoes, but they are associated with rock on rock. So we get these powerful earthquakes, which often can be very close to the surface. So a powerful earthquake close to the surface is not a very healthy thing to experience. Now convergent boundaries. Basically, what we expect to find with a convergent boundary is a trench. Usually, we find island arcs and folded mountains, explosive volcanoes, and deep, powerful earthquakes. So those are the things we would associate with a convergent boundary. Now, it turns out there's three different types of convergent boundary. You can have ocean, where ocean material is going underneath ocean material, ocean continent, or continent. Let's look at each of these. So ocean, I have ocean crust here and ocean crust sinking underneath it. So I'm going to get a trench. I'm going to get this partial melting. I'm going to get violent, powerful earthquakes going to depths of up to 700 kilometers. About 300 kilometers in, I'm going to get volcanoes forming, and these volcanoes are going to be very explosive because there's a lot of water and shell material here that's going to provide the steam and carbon dioxide. And we tend to form what are called island arcs. So that's what we associate with ocean convergence. Now, ocean-continent convergence, again, we'll have a trench, we'll have powerful deep earthquakes. 300 kilometers inland, we're going to have violent volcanic activity because, again, I have oceanic crustal material that has water and shell material, and so it's going to cause the explosive volcanic eruptions. But the other thing I tend to get here is, as this pushes against the continent, we tend to get folded mountains, large mountains that are non-volcanic in nature with volcanoes scattered among them. And then we can have continent. And the best example of continent is the Himalaya mountain ranges. What happened was there's an ocean basin that basically got subducted away. It is gone now. So basically, the ocean, this is the ancient ocean crust is all the way under. There's nothing left. There's just continent behind it. And so I have the continent push against the continent. So I'm not going to get any more melting happening because this can't go down anymore. And so instead, this just gets pushed up. So we get this high plateau. We get these very large folded mountains, and we tend to get earthquakes. But these earthquakes don't go down very deep. They tend to be fairly shallow earthquakes, but still fairly powerful. These are the symbols that we use on maps sometimes to represent these two parallel lines indicate a divergent plate boundary. These teeth indicate a trench where we have subduction, and the teeth point in the direction that the plate is plunging. And transformed plate boundary uses these arrows that kind of look like you use in chemistry when you're talking about orbitals. Right? And last thing, sorry this goes so long, then this that we call hotspot volcanism. So a hotspot, and Hawaii is the classic example of this, is a place where we have volcanic activity that is not associated with a plate boundary, which is very unusual. For whatever reason, there's an area of the mantle that's very hot, and just since there's one plume of magma that pokes right through the lithosphere and erupts as a volcano. There's quite a few of these on our planet. Hawaiian Islands are the most famous of these. And I think that's got it. I think we're done. Let's see. Oh, and the last thing I want to say, I'm making a screencast, hang on a second, is that these tend to not be very explosive volcanoes, and the reason is because there's not a lot of water or shell material to give us carbon dioxide, so they tend to be very liquidy, flowy types of volcanoes. And I believe that is the end of this. Yes, thanks for watching.